This video is on thermodynamics, specifically entropy, second and third law, and statistics. Question 1. Define entropy. Units? So this is a controversial question. You may get different answers to this. Most textbooks define entropy as the disorder of a system of particles. So example, more particles and more volume means more possible arrangements and therefore more entropy. So using the equation delta S equals delta Q over T from the physics data booklet, the units of entropy is S equals joules over Kelvin. Question 2. Describe the equation delta S equals delta Q over T. If the temperature of an object is held constant, then we can determine the change in entropy of the object when energy flows into or out of it. Question 3. The change in entropy of a system is defined as delta S equals delta Q over delta T. What can we do to make delta S positive? Well, we could melt an object. The temperature must be constant to use this equation. Part B, what can we do to make delta S negative? Well, we could freeze an object. The temperature must be constant to use this equation. Question 4, a cup of hot chocolate at a temperature of 90 degrees is in a room with an ambient temperature of 23 degrees Celsius. If the temperature of the hot chocolate and room do not change, and 1.97 times 10 to the 3 joules of energy flows out of the hot chocolate to the room, then determine the change in entropy. So the hot chocolate lost energy. And the temperature needs to be converted to Kelvin. So this is how much energy was lost by the hot chocolate. And in turn, this is the amount of energy that was gained by the room, or entropy that was gained by the room. And we do have a total change in entropy. Question 5. Two large cubes filled with water are separated by a thin thermally conducted metal plate. The temperature of the water in cube 1 is 82 degrees Celsius and the temperature of the water in cube 2 is 39 degrees Celsius. Determine the change in entropy of the whole system of heat flows between the plate. At 249 joules per second. So remember, energy goes from hot to cold. So cube 1 is going to lose energy and cube 2 is going to gain energy. That's why cube 1 has a negative sign here. And that's why cube 2 has a positive sign here. And this is the change in entropy of the whole system. You just subtract the two. Question 4. 400 grams of ice at 0 degrees Celsius melts to water at a constant temperature. The latent heat diffusion of water is 3.34 times 10 to the 5 joules over kilograms. Determine the change in entropy. So Q is equal to ml, or delta Q is equal to ml. And convert degrees Celsius to Kelvin. Since we are going from a solid to a liquid, then the entropy increases. Question 7. 500 grams of water at 0 degrees Celsius freezes to ice at a constant temperature. The latent heat of fusion of H2O is 3.34 times 10 to the 5 joules over kilograms. Determine the change in entropy. So Q equals ml, and delta T is in Kelvin. And since we're freezing, we're going to decrease our entropy. So our solution is negative. Question 8. 600 grams of boiling water at 100 degrees Celsius vaporizes to steam at a constant temperature. So we're going to go from liquid to gas. That's why the change in entropy should be positive. The latent heat of vaporization of H2O is 2.26 times 10 to the 6 joules over kilograms. Determine the change in entropy. So delta S, once again, equals delta Q over delta T, and we get a positive solution. Question 9. 800 grams of steam at 100 degrees Celsius condenses to water at a constant temperature. The latent heat of vaporization of water is 2.26 times 10 to the 6 joules over kilograms. Determine the change in entropy. So steam, which is a gas, condenses to water, means becomes a liquid. So we're going to decrease our amount of entropy. So that's why the solution here is negative. So delta Q is given to us, the mass is given to us. We just have to convert degrees Celsius to Kelvin. Question 10. A piston is slowly compressed, so the temperature of the ideal gas inside it remains at 40 degrees Celsius. 748 joules of work is done on the gas. Determine the change in entropy of the gas. Well, Q equals delta U plus W. Delta U is equal to 0 since it's an isothermal process. So Q equals delta W, which is minus 748 joules. This is negative because it was compressed. So delta Q is minus 748 joules. And delta S is negative. This is important here. The disorder of the gas is decreased since the gas is pushed to a smaller volume and there is a negative sign in the solution. Question 11. A piston is slowly expanded so the temperature of the ideal gas inside it remains at 68.3 degrees Celsius. 498 joules of work is done by the gas. That means it gets bigger, the volume. Determine the change in entropy of the gas. Q equals delta U plus W. The temperature remains constant, so delta U is equal to 0. Q equals W, which is plus 498 joules. So delta S equals delta Q over delta T. And our solution is positive, because work done is positive. So there's more disorder. Question 12. Describe the equation S equals K sub B ln omega. This equation tells us the entropy of a system. So S is entropy, disorder. K sub B is a constant, Boltzmann's constant, and omega is equal to the total number of possible microstates. So here are some examples. Rolling one dice gives 6 possible microstates. Rolling 2 dice, one at a time, gives 36 possible microstates. And S is directly proportional to omega. So as omega increases, S increases. Question 13. Determine the entropy of a system which has 7.53 times 10 to the 45 microstates. So we know K sub B is a constant, and we're given omega, so we could solve for S. Question 14, state the second law of thermodynamics. So there are many different ways to express this law. The second law of thermodynamics states that the total entropy of a system will stay the same or increase during a process. Energy or heat will transfer from higher to lower. And when energy or heat transfers from a hotter object to a colder object, then there is less ability to do work. This is important. Recall that two objects in thermal equilibrium have the same temperature, and therefore no energy or heat is being transferred between the two, so no work is being done. Question 15. State the Clausius version of the second law of thermodynamics. Heat will not flow from a colder object to a hotter object. And it takes work to transfer energy from a colder object to a hotter object. This is how a refrigerator works. Question 16. State the Kelvin version of the second law of thermodynamics. You can never have a 100% efficient engine. Question 17. State the arrow of time and entropy in terms of the second law of thermodynamics. As t goes to infinity, S goes to infinity. This is also called the heat death of the universe. Question 18. State the third law of thermodynamics. The entropy of a perfect crystalline solid at absolute zero is 0 joules over Kelvin. Question 19. Describe the equation PV to the 5/3 as a constant. The adiabatic change of an ideal monatomic gas is given by the following equation. PV to the 5/3 is a constant. Question 20. An ideal gas is initially held at a pressure of 1.23 times 10 to the 4 pascals, a volume of 9.06 times 10 to the 1 meters cubed, and a temperature of 348 Kelvin. The ideal gas then expands adiabatically to a new volume of 1 times 10 to the 1 meters cubed. Determine the final pressure and final temperature of the ideal gas. Since this is an adiabatic process, we can use the following equation here. We were given V1, V2, and P1, so we could solve for P2. So we have the final pressure. Now we're going to use the ideal gas law to solve for temperature 2. So notice that the final pressure and final temperature both decrease during this volumetric expansion. Temperature goes from 348 to 326. Pressure goes from 1.23 times 10 to the 4 to 1.04 times 10 to the 4. Question 21. An ideal gas is initially held at a pressure of 7.65 times 10 to the 4 pascals, a volume of 9.63 times 10 to the minus 1 meters cubed, and a temperature of 388 Kelvin. The ideal gas then compresses adiabatically to a new volume of 8.28 times 10 to the minus 1 meters cubed. Determine the final pressure and final temperature of the ideal gas. Once again, since this is adiabatic, we can use this equation. We could solve for P2 since we're given volume 1 and volume 2 and P1. Finally, we could use the ideal gas law to solve for temperature 2. So we're being compressed here, so temperature increases and pressure increases. Question 22. In an adiabatic process, the volume of a piston increases from 145 to 194. By which factor does the pressure change? Okay. Changes by this much. We're just using the same equation. Question 2. In an adiabatic process, the pressure of a piston increases from 3.03 times 10 to the 5 pascals to 7.07 times 10 to the 5 pascals. By which factor does the volume change? Question 24. Define heat engine and heat pump. A heat engine converts thermal energy to mechanical energy. Heat moves from a hot reservoir to a cold reservoir. A heat pump moves heat from a cold reservoir to a hot reservoir. A common example of a heat pump is a refrigerator. So question 25, use a pencil. Carefully and clearly draw the Carnot cycle. Label the vertical axis and the horizontal axis. Label the adiabatic processes and isothermal processes. So we have 4 steps. Step 1 is an isothermal process, which is slow. We have volumetric expansion. Step 2 in green is an adiabatic process. That's a fast process. That's also a volumetric expansion. Step 3, we have another isothermal process. It's slow and it's a volumetric compression. Finally, step 4 is the blue process. We're decreasing the volume, which is a volumetric compression, and that's a fast process. So in steps 1 and 3, the temperature is constant. In steps 2 and 4, the temperature is not constant. We go from one isotherm to another isotherm. Question 26. In general, the efficiency of an engine is N eta equals useful work over input energy. For a Carnot engine, N Carnot equals 1 minus T hot over T cold. So is the Carnot cycle a fast or slow process? It's a slow process. Is it realistic? It's not realistic because it's slow. Is it efficient? It's the most efficient cyclic process we know. Question 27. Calculate the efficiency of a Carnot engine operating between the following temperatures. So you could see the difference between A, B, and C, the change in temperature is only 100 degrees Kelvin or 100 degrees Celsius. But you see, as the temperature increases, eta Carnot, the efficiency of a Carnot engine decreases. So when we go from 123 degrees Celsius to 23 degrees Celsius, the efficiency is 0.253. But when we go from 323 to 223, the efficiency decreases to 0.168. Question 28. Suppose you have 12 two-sided fair unbiased coins. So they could be heads or tails. 50-50. You throw them all up and count the number of heads and number of tails. You want to determine the number of arrangements to land 1 head, 2 heads, 3 heads, etc., and also its probability. Complete the table below. So please ask your math teacher about this problem. This is statistics. So this is a quick question, a lesson about factorials. 0 factorial is equal to 1. Don't ask why, just memorize it. 1 factorial is equal to 1. 2 factorials is equal to 2 times 1. 3 factorial is equal to 3 times 2 times 1. 4 factorial is equal to 4 times 3 times 2 times 1. And 5 factorial is equal to 5 times 4 times 3 times 2 times 1. We cannot take factorials of negative numbers. So just memorize that. So what's the probability of us having 12 coins, throwing them all up, and getting 0 heads? So all tails. This is the equation. Okay. So the probability is 1 over 4096. Okay. Number of heads, as you could see, the numerator is always 12 factorial. And the denominator, the first term in the denominator is number of heads. The second term is number of tails. So when we have, for number of heads being 1, that means 1 head, 11 tails. Look at the denominator. It's 1 factorial times 11 factorial. So there's 12 different ways we could get 1 head and 11 tails. We could get head and then 11 tails. We could get tails, head, and then 10 tails. We get 2 tails, 1 head, and 9 tails, and it goes on. So this is the probability. 3 over 1024. If we want 2 heads and 10 tails, there's going to be 66 ways we can do that. So the probability is going to be 66 over 4096. And you could see we are most likely to get here. There are 924 possible ways to get 6 heads and 6 tails. The second most popular way is to get 5 heads and 7 tails, or 7 heads and 5 tails. They're equal. And then the next most probable way solution is 4 heads and 8 tails, or 8 tails and 4 heads. And it's least likely to get 12 tails. 12 tails and 0 heads. This is 0 heads and 12 tails. This is 12 heads and 0 tails, which are equal to each other.